Hi everyone. So today we are going to discuss about the magnetic field, and this is the second unit. Here we will discuss about the magnetic field and its application to Ampere's law. Then we will discuss some examples of Ampere's law using toroid and solenoid and Helmholtz coil, and we will find how can we calculate the magnetic field. So what are the sources of the magnetic field? The sources of the magnetic field is generally the current. And the current, when we will discuss to the current, we will definitely come to the charge. So when the charge is moving and it changes with respect to time, we have I equal to dq by dt when t is going to 0. So again, the magnetic moments, we will see that how the conductors behave as a magnetic dipole. When a circular coil, we will discuss later how the circular coil will shows the magnetic poles behavior and hence the creation of the magnetic field. Time varying electric field. So this is important. The electric field, the time varying the electric field. This time varying electric field will see how the electric field changes will create the magnetic field. So there is a strong link between the electric field and magnetic field. If electric field fluctuates, then we will see how the magnetic field has changes. So an electric field acting on a charge produces a force, definitely. Like as the electrostatic force we have discussed, that F is equal to QE. So the field will generate the electric force. So similarly here magnetic field also generate the magnetic force, and its quantity equal to Q into V cross B. So what is the B? Now when a charged particle will go through the magnetic field, it will act by a force due to the magnetic field, and that will create the magnetic force. So this is the magnetic force due to magnetic field and the charged particle moving inside the magnetic field. So what will be the direction of the magnetic force? The direction will be perpendicular to both magnetic field and the velocity vector. In the presence of both electric field and magnetic field, we will see a net force that is called the Lorentz force, and the expression of Lorentz force is equal to QE plus Q into V cross P. So the direction, you notice to the direction that the electric field is along the force direction, that is the force is along the electric field, and that electric field is perpendicular to both velocity and magnetic field. Then the substitution will be same. So it recommended that the magnetic force does not exist unless the charged particle is moving. That is, magnetic force will not exist if there is no velocity. So when there is velocity, there will be existence of magnetic force. And even no work is done as the force is perpendicular to the motion of B. So if motion is not there, there will be no magnetic force, hence no work will be done. Now let's see what is the force on current carrying conductor. When a conductor will carry the current, we will see how much the force will act. The force on a charged particle, we see that F is equal to Q into V cross P. Now here we will see how current carrying conductor force will be acted. So when in a conductor there will be charged particle flowing with velocity V, we cannot measure that how many number of charged particles here, that is different, but we can consider or we can mark as the linear charge density lambda. So lambda is the linear charge density. This is the charge by unit length. So there is a relation of speed v constitute a current. When a charged particle moving with velocity v in a conductor, it will experience a current. That current is lambda into v. What is lambda? This is a linear charge density, charge by length, and you see the relation I equal to dq by dt. How if you will change the dl, that dq by dl and dl by dt, so that dl tends to 0. So dq by dt our is current. So our d lambda is equal to dq by dl. This is the charge per unit length. this is the linear charge density. So remember the relation I equal to lambda into V. Lambda is the linear charge density and V is the charge moving inside the conductor. So magnetic force on a segment of current carrying wire is, what is the magnetic force? We know that Q into V cross B. This is the charge particle moving inside with velocity V in a magnetic field B. So the integration over dq will give us the total magnetic force. So now change I equal to lambda into B, and the changes will be give V cross B into lambda dl. That is simplification. We see the simplification below, that F is equal to magnetic I into dl cross B equal to I into dl cross B. How the changes? The points to note it, that B cross B into lambda dl, because dq is equal to lambda dl. Here we can see that dq equal to lambda dl. So that lambda dl, lambda the charge per unit length. So here changes, the lambda is the constant. When you give to lambda into V, that lambda V will give us the current. So that V cross B into lambda changes to I cross B into dl. So this is the expression. I cross B into dl is the magnetic force due to a current carrying conductor. We all know about this expression, but this is the derivation from charges to the current when the charges is flowing with a linear charge density lambda. Then we'll remember some things, that the current density, that is the current per unit area. Current density is the current per unit area. Current is scalar quantity, but the vector represents the perpendicular to the surface. So this is the current per unit area, and rho is the volume charge density, the charge per unit volume. So how the relation J equal to rho V, that comes from Ohm's law. If we will solve it, then it will give J equal to rho V. Remember also this formula. This is volume charge density. This is current density. This is volume charge density, but this is current density. I multiplied with the velocity. So next go to the magnetic force. So what was the magnetic force? This is some different expressions of magnetic forces. So Q into V cross B, that dq integration will give the total magnetic force. So V cross B into rho V, because rho is equal to Q by B. So dq is equal to rho dV. This is the surface is the volume charge density. So rho into V will give us J equal to rho V cross B dV. And we have I equal to J into dA, because J is equal to I by A. So I will give J into dA. This is a surface integral. This is the equation of continuity. We will see it later in the next unit. So equation of continuity gives del dot J plus del rho by del T equal to 0. Next come to Biot-Savart's law. We all know about this law, so I am not going to describe about this law. We go direct to the expression. There is a current carrying wire which are carrying current I, and we want to calculate here the magnetic field which is at a distance r from the origin. And here we are going to calculate due to a small current carrying element, not to the whole wire. We will calculate for a simple element, and if we will integrate over its path, then it will give us the total magnetic field. So this is the vector addition rule. From where we are going to calculate, the direction will be towards the point where we are going to calculate from the origin. So the direction is towards the point. Hence this is let this is where r and this is where prime. So this will give us r minus r prime. It's the vector addition. This is in same direction and this is the opposite direction. So theta is the angle where we are going to calculate the point, and the dl vector that perpendicular to the surface, to the path. So how the magnetic field due to current carrying element, proportional to the current and is proportional to sine of the angle and is proportional to inversely proportional to the square of the distance, and is directly proportional to the length. So this simplification will be multiplied by a constant. That constant later will come as mu 0 by 4 pi. That quantity is 10 to the power minus 7 decimeter per ampere. So remember the magnetic field direction. This is perpendicular to the direction of the point where we are going to calculate the magnetic field and the dl. So these are other alternative form of the magnetic field, that dB integration over the path will give the total magnetic field, and that I dl into r minus r prime. We will simplify, then this will give the current density into r minus r prime by r minus r prime q into dB prime. This is a volume integral, not path integral. This is volume integral. And remember how the current density is due to the current carrying wire, means the element. So that's why here I prime is there. Just focus to the formula. Here B is a function of r in general coordinate x, y, z, but j is not coordinate of the point where we are going to calculate, but r prime is the coordinate of the current carrying element, its current carrying element's path, and r minus r prime is the distance. So there is two coordinate, one r coordinate, another is r prime coordinate. This will help us to calculate the gradient and divergence of the magnetic field. So remember this formula. And how this is come out, I just focus to this relation, ideal sin theta by r square, ideal cross r, and dl cross r, how the dA coming. So j cross r minus r prime by r minus r prime q into dB prime. This is in current density formula. If you will simplify using the formula of current density, you will get the volume integral, and that's not a big problem. So the path integral, another formula we have to remember, that the curl of the magnetic field is equal to the magnetic permeability into the current density, del cross B is equal to mu naught J. So B dot dl is equal to del cross B dot n cap ds, and there will be a double integral. Actually this is a surface integral, not path, but this is path integral, when ds n cap is there perpendicular to surface. So this is our Stokes theorem, the path integral to surface integral, the Stokes theorem. And del cross B, remember that mu naught J. This will be discussed later, the curl of the magnetic field. So mu naught J dot n cap ds. What is J dot n cap ds? This is nothing but the current, because mu 0 is constant, so mu 0 I. So B dot dl is called mu 0 I. This is nothing but the Ampere's law. We will later discuss. So remember these three formulas. You already known it, that due to a finite wire, mu 0 I by 4 pi d into sin theta 2 minus sin theta 1, or you can change it to cosine theta 2 minus cosine theta 1, taking the theta angles. So that's not big, and this is due to an infinite long wire, mu 0 I by 2 pi d, and this is the force due to two parallel wires, mu 0 by 2 pi, I1 I2 by d. I1 I2 are two currents. If they are flowing in the same direction, then they will attract. If they are flowing in the opposite direction, they will repel. These all are known in our CHSC level. So this is Ampere's law. Next, go to the magnetic dipole. So this is an important, because all the previous things we already known from the CSS level. But the magnetic dipole, how a current carrying loop will create a magnetic dipole. So this is the important thing. When we discuss the electrostatic, the charge particle, the opposite charges, means 1 plus 1 minus, when they are separated by a small distance, they created electric dipole. But in magnetic dipole, same things, but the polarity is different. Different polarity, and separated by a small distance will create a magnetic dipole. And what is the expression of magnetic dipole? A current into area. Suppose a current carrying, here we will discuss how a current carrying element, wire how a current carrying wire will behave as a magnetic dipole. So when we will take a current carrying loop, then the flowing current I and A is the area. So the magnetic pole direction, its magnitude will be current into area. And what is the direction of the magnetic dipole? The direction of the magnetic dipole will be perpendicular to the surface. It means the normal to the surface. So magnetic dipole direction is perpendicular to the surface, and its quantity is I into area magnitude. So if we will simplify, what is the current and the current density? Current density is called current into area, current divided by area. So if we will divide this divided by area, then same expression will come, that R cross JR into dqr. This is the volume integral, and we will see how the magnetic moment, M is the magnetic moment, this is not dipole, this is magnetic moment. The construction is magnetic dipole, but M is the magnetic moment, not magnetization. Magnetization is magnetic moment by volume, but here the magnetic moment is current into area, and the direction is perpendicular to the surface. Then how a electric wire behaves like a magnetic dipole? We'll see here that every magnetic element has a north pole and south pole. We know that its direction is north pole to outward and south pole to inward. So this is a wire. Look to the direction. This current is flowing, and the north pole is and south pole, they are different. The north pole to outward and south pole to inward. So the current is flowing in this way. So remember, when current is flowing through the wire, this pole, these two sides, one side is clockwise rotating and another side is anti-clockwise. Focus to the points. The downward is the clockwise and the upward is the anti-clockwise side. So when the top level is in clockwise side and the down is in anti-clockwise side. So when the current is flowing in clockwise, you can consider that when we will rotate a knot or a screwdriver to clockwise, it will move to downward. But when we will move in anti-clockwise, it will move upward. So when it is going to downward, that is the south direction. But when it will move to anti-clockwise, means upward, it is in north direction, like positive Z and negative Z. If it is moving to downward, then this is negative Z. And if it is moving to upward, then that is positive Z. So remember here 2 points, that when it is moving in clockwise, it will move to downward, means south. And when it is in anti-clockwise, it will move to upward, means north pole. So in a current carrying wire, how it will behave in a magnetic behavior? So we look to the current direction, that how it is clockwise or anti-clockwise in a single current wire. So we'll find out that two poles are there in a current wire. So if this is completed, then look to this diagram, that this is current carrying loop, how north pole and south pole are generated. So we define the magnetic dipole moment to be a vector pointing out the plane. So its direction is outward to the plane, means the normal direction, and with a magnitude equal to product of the current and the loop area. It also can be related as mu. So these are two formulas, in R and theta. If you will mathematically solve, then you will get these formulas. So Ampere circuital law. I already told about this, that how the Ampere circuital law can be derived. So this is from Stokes law coming. B dot dl will be del cross b. B dot dl will be del cross b dot n cap ds. That del cross b is nothing but mu naught j, and j is nothing but I by area, so there will be cancellation and we will get directly mu 0 I. But here also can be discovered like this, that the magnetic field due to a current carrying loop is equal to mu 0 I by 2 pi r, and if we will solve, then we will get mu 0 I into enclosed. So this is looks like the magnetic flux. So B dot dl, the path integral over magnetic field, is equal to mu naught into the current enclosed by this path. Remember, the path integral, the line integral of the magnetic field over a path is equal to mu naught into the current enclosed by this path, where I enclosed is the total current enclosed by the Amperian loop, means the Ampere loop, this loop. So we have to, same thing, we have to close the path and then we can apply the Ampere circuital law. So next we will see how this Ampere circuital law can be used in a toroid case and in solenoid case and Helmholtz coil to find out the magnetic field. The line integral also we can use here, the Stokes law. Previously we have discussed how the law used here. B dot dl, that del cross b dot n cap ds, then, but we didn't derive still now del cross b equal to mu naught j. So this is simplification. Del cross b mu naught j, j is equal to I by area. So here area will be cancelled and mu naught I will be remain. So B dot dl equal to mu naught I. Otherwise, using this formula, B equal to mu 0 I by 2 pi r for a circular loop. But this is for circular loop, Ampere circuital law, and this path is enclosed. So we cannot take for a single element. So B dot dl equal to mu 0 I by mu 0 I enclosed. So let's again follow to the path. So this is magnetic field. What are the sources of the magnetic field? Then what is magnetic force? Just remember the formula QV cross B, and this is Lorentz force. Then magnetic force due to a current carrying conductor or current carrying wire. Then the current density, volume charge density, and how they are related. J equal to rho B. Then the magnetic force equation of continuity, this is a big equation, del dot J plus del rho by del T equal to 0. One is space variance and another is time variance. Then Biot-Savart's law, and then the formulas of using Biot-Savart's law, how you can calculate. So this is out of syllabus, CSCC level, so you have to remember this formula. Then the magnetic dipole, this is important. Remember the magnitude I into area, and the direction is perpendicular to the surface. Then Ampere circuital law, B dot dl equal to mu dot I. So the law you should write in mathematical expression that the line integral or the path integral of magnetic field over a closed path is equal to mu naught the magnetic permeability into the current enclosed by this closed path C. So in the next we will discuss about the application of Ampere's law. Let's stop there.